So in the previous video, we took a look at the second fundamental theorem of calculus, which told us that if we have a function f of x, lowercase f of x, that's defined as the derivative of some other function, capital F of x, so f prime of x over here, capital F prime of x, then the integral from a to b of f of x dx is just given by capital F of b minus capital F of a, and we can condense that into this notation right over here. So essentially, it tells us that the definite integral of a function is given by its antiderivative evaluated at the two endpoints, and then the difference between it evaluated at those two endpoints. And so we're going to use this definition now to actually determine a couple of different properties of definite integrals. And so I'm not going to prove all of these very rigorously myself. I'm going to leave some of these up to you. But the whole point is just to get comfortable with these different properties so that we can actually start applying them in order to solve different definite integrals without just having to use our geometric properties. And so let's go ahead and actually do that. So here we have the definite integral from a to b of f of x plus or minus g of x dx. And so if you wanted to prove this for the case of, just f of x plus g of x, you can do that separately, or the case of f of x minus g of x. I'm just going to do the first case. And so if we consider minus, or f of x plus g of x, then this would be the definite integral from a to b of f of x plus g of x dx, right? And we don't really have to put parentheses around the f of x and the g of x. And then this is just going to be what? This is going to be capital F of b plus capital G of b. And then we're going to subtract that, so I can put parentheses here. We're going to subtract that from capital G of, or from capital F of a plus capital G of a. And then if we distribute the negative sign, we get capital F of b minus capital F of a. And then here we get, so I can put that in parentheses, plus capital G of b minus capital G of a. And we recognize this, right? This is just the integral from a to b of f of x dx, and this is the integral from a to b of g of x dx. And so this just ends up being the integral from a to b of f of x dx plus the integral from a to b of g of x dx. And so ultimately, we can say that this integral right over here is equal to the integral from a to b of f of x dx plus or minus the integral from a to b of g of x dx. So whenever you have the sum or the difference of two functions, then you can actually separate the integrals. And it only holds for the sum or the difference, not for the product or the quotient. You can prove it for the negative case if you would like. It's basically the same proof. Then the next one we have here is a constant times f of x, so the integral from a to b of k times f of x, right? And so we know right over here that f of x is equal to capital F prime of x, right? And so we know that also the derivative is a linear operator, so when we multiply by a constant, it doesn't really impact the constant, kind of can just be taken out of the derivative. And so this is going to be k times f of b minus k times capital F of a, which we can factor that k out and we get f, I'm just going to write it like this, f of x evaluated at from b to a. And then we know that this right over here is just the definite integral. So this is k times the definite integral from a to b of f of x dx. And so you can actually factor out a constant whenever you are taking a definite integral. You can take the constant out and it doesn't really impact the integral at all. So that's another very interesting property. And then the negative integral from a to b, or the negative of the definite integral from a to b of f of x dx. Again, we can keep that negative outside, and this will just be capital F of b minus capital F of a, which is equal to f of a minus f of b if we just distribute the negative sign. And what is this? This is just, this right over here is just equal to the integral from b to a of f of x dx, right? So we swapped the bounds of integration when we took the negative. That's another very crucial property. And then here we have the definite integral from a to b of f of x dx, and here we have some constant c that's located between a and b. And it actually turns out, so we can write this as f of b minus f of a, and then we can go ahead and add and subtract capital F of c, right? We can do this because we're not really changing the value right over here. We're adding and subtracting, so we're keeping it the same. And then what we can do is we can kind of reorganize everything. We can write this as capital F of c minus capital F of a plus capital F of b minus capital F of c. Again, we aren't changing anything, we're just reordering it. This right over here becomes the integral from a to c of lowercase f of x dx. And then this right over here becomes the integral from c to b of f of x dx. And so that's another interesting property, is when we have a constant in between the bounds of integration, that we can actually separate out the integrals into two separate integrals. It's like breaking up the area into two separate parts, if you want to think about it geometrically, which we actually did do when we were evaluating integrals using our geometric properties. And then finally over here, the integral from a to a of f of x dx, we know that this is just going to be f of a minus f of a, right? Very simple. This is going to just be equal to 0. And this makes sense, again, geometrically, because if we're integrating at one point, then it's just a straight line down, right? And we know that the straight line will have an area of 0, so we can say that this is going to be equal to 0 for all given a and f of x. And so these are just a couple of different properties for definite integrals. Again, I encourage you to go ahead and try proving these for yourself so you can get a little bit more of a rigorous understanding of these properties. But honestly, they are quite intuitive, and they are going to become very helpful when we actually do, evaluate definite integrals by hand.